Hi, I'm Antonio Sale, and in this video we are going to discuss how to design suitable control structures, say cascade, feed-forward, ratio control or whatever, for this two-tank system. We will first discuss the problem statements, which are the primary control goals, and then we'll start by devising a simple multi-loop structure, thinking in the pairing problem by just common sense. In that simplified structure, we will use only a subset of the available sensors and manipulated variables, and in a second sequel video, we'll devise a more complex control structure which uses all the available instruments. That will be left for a second video for brevity. So let us start by describing in lay words why we are considering this control problem. Well, the basic idea here is that a reagent must be diluted in water and also it must be heated to a given temperature. So the goal of this process is meeting a downstream demand with whatever flow they wish of this diluted reagent at a given concentration and a given temperature. That downstream demand can be measured by the flow transmitter 3 in this figure, if so wished. Indeed, we will use that flow sensor in the second video for feed-forward compensation, because the downstream flow demand is a disturbance. So we have two basic primary variables to control, which are outlet temperature, measured by the TT2 sensor, and the outlet concentration, measured by the analysis transmitter 8T. Apart from those two primary controlled variables and measurements, we will also set up a given setpoint value for the level, in particular tank 1 level. Tank 2 will be slightly lower, possibly. That level will be also considered to be a primary control variable with a set point from the operator console, and somehow it is related to safety considerations. Tanks must not overflow or must not get empty when there is increase of demand, and also for control purposes, in the sense that if the tanks are emptier than expected, then the residence time of the involved fluids decreases. So the time constants of the plants are faster, and that maybe would need changes in the controller gains. So in order to avoid that situation, it's convenient to set a constant level set point apart from the previously mentioned safety considerations. So, in summary, our three primary controlled variables are output temperature, output concentration, and the level of the left tank. Good. So, how can we achieve those control goals? Well, in this picture we have a total of 7 sensors, 3 flow sensors, 2 temperature sensors, 1 concentration sensor and 1 level sensor, and we have a total of 4 manipulated variables. The heating power in tank 2, which is labeled as VM1, manipulated 1, a water valve, VM2, a reagent valve, VM4, and a steam supply valve, VM3, to a heat exchanger in order to heat the water inflow before entering tank 1. So with 7 sensors and 4 manipulated variables, we have sort of an excess of instruments if we just wish to control 3 things. Indeed, this is the case, so we will first devise a simple 3 sensor, 3 controller, 3 manipulated variables structure, a plain multi-loop one with no bells and whistles, and supposedly we would test that structure either in simulation or in real experimentation, and if performance is not satisfactory, then we would decide to buy these additional instruments to improve performance. That will be the assumption of the second video. In here we have just described which is the problem, and then we will just think on the most simple solution for the moment being. So let us discuss temperature, level and concentration control. In order to get some common sense assessment on what to do, we will assume that the nominal ratio between reagent flow and water flow, let's say, is 1 to 5. 1 liter of reagent per 5 liters of water. Why am I saying that? Well, because basically this will mean that the flows will be used in the case of the reagent to control concentration, and in the case of the solvent water to control level. Why? Well, because if I increase 1 unit the reagent flow, then for instance, if instead of 1/5 I increase to 2/5, then the concentration will increase from 1/6 total reagent concentration to 2/7. This is a big increase. On the other hand, if I increase water from 5 to 6, then the concentration will decrease from 1/6 total proportion of reagent to 1/7. Then this is a much smaller increase if you compute that. So grossly speaking, the flow to concentration gain of the inflow with lower nominal flow figures is the one that most influences concentration, and conversely, we can do it formally with some formulas and some relative gain array computations, but as we don't have a model and this is just of common sense, just get with the idea that high flow is used for level, water in this case, and low flow is used for concentration control, the reagent in this case. So once we have this discussion on pairing by common sense argumentations, the most simple control strategy will be sending this analysis transmitter output to a suitable controller and then acting on this valve. Level measurements will be sent to a level controller actuating on this valve, and then now we have to think on what to do with temperature. So this temperature sensor will transmit its value to a temperature controller, and then the thing is that we have 2 remaining manipulated variables, either the steam valve in the inlet heat exchanger or the heater in the second tank close to the outlet pipe. So which one should we use? Well, there are some advantages and disadvantages on each of them, and of course it also depends on the dimensions. On the one hand, common sense argumentation would tell that I would choose as a manipulated variable an actuator with fast dynamics and large effect on my controlled variable, high gain, high bandwidth, low time constant. However, we can imagine that in this case our VM1 actuator will be fast because it's heating a small tank close to the outlet pipe. But let's say if this is an electrical resistor, then maybe a large steam controlled heat exchanger might be more powerful. So we will assume that VM1 is fast, but maybe it does not have enough gain, and VM3 has a lot of gain, a lot of effect on the water temperature, but it is slow because we must heat the metallic masses of the heat exchanger, and then we must fill tank 1 with hot water before such water reaches tank 2. So it will have a large dead time or time constant. Then how can we control? Of course, in the second video we will use both of the actuators in a cascade configuration, but in here we will just assume that as a first thing to be tested, we will choose the fast and close to the output option. So this temperature controller will send a power command to this heating element. And hopefully, if set point changes and disturbances are small enough, then not using this VM3, setting that to a manual constant operating point, maybe we have enough control capacity to reject whatever disturbances or to track whatever small enough set point changes. So this is it. We have made a decision on this multiloop structure with a concentration control in cyan, temperature control in magenta, and level control in orange, with pairings arising from common sense reasoning, and in the case of temperature control, favoring the fast actuator for easier tuning and hoping that the needed temperature increments are small enough. We are not using any of these extra flow sensors, none of the three, and we are neither using this extra temperature sensor. So we have dismissed those 4 sensors and this actuator, hoping that maybe performance is good enough for my customer, and in such a case saving money from the upfront cost of these instruments and their installation and the more complex control structure needed to use them. So this would be the multiloop structure to be, let's say, field tested. If performance is good enough, problem would be finished, and if performance is not good enough, then we'll need to make use of this additional instrumentation to achieve the requested performance improvement. But we'll do that in a sequel video. For the moment being, we end here. Thanks for watching.